So this video is a video that's going to cover two subsections of the notes. I'm going to try and cover subsection 8.1, which is an introduction to continuous random variables, and subsection 8.2, which talks about the most important defining characteristic of them, which is something called a probability density function. So in the past three sections of notes, we've looked at discrete random variables. And discrete random variables took finitely many, or perhaps countably infinitely many, different discrete, separate outcomes. And we could think of those discrete, separate outcomes as modelling count data, as in things that you count. Here we're going to be looking at continuous random variables. And here the values that they can take is a range, a continuum of gradually varying values. So they will be uncountably infinite. And so we're thinking of this as something that you measure rather than something that you count individual values. To give some examples, say the assets of a bank, if we count things in credit as being positive numbers and things in debt as being negative numbers, then we can model the assets of a bank as a real number that continuously varies. It doesn't just take discrete blobs. And so this would be a continuous random variable to represent that varying measurement. If we're looking at the amount of time that we get a new machine until it breaks, that can be any positive amount of time. So that would be a positive real number. But again, we're talking about a gradually varying continuum. And so we're talking about a continuous random variable. For a third example, something like a proportion, say the unemployment rate in the UK. That proportion will be a number between 0 and 1, right, between 0% and 100%. So that would be an interval from 0 to 1, but because it could vary anywhere in the continuum between 0 and 1, that would be continuous and not discrete. So those are the kind of things that we're looking at here. So when we did discrete random variables, we also said, like, what's the probability that you exactly hit a certain value? What's the probability exactly equal to 1 or exactly equal to 2? But that's not how we think about things in continuous random variables. Imagine that you're firing an arrow at a big, like, circular target. What you don't really say is, what's the probability you hit this exact point on the target? It's not even clear what that means. If you mean by point a kind of mathematically perfect, infinitesimally tiny point, then you'd have to say that the probability of exactly hitting it is 0, right? You know, that you nestle exactly between the atoms or whatever. But it almost doesn't make sense to ask. What makes more sense is to, like, draw a shape on the target, like a circle in the middle, which we call the bullseye. And we could say, what's the probability that the arrow lands inside that shape in the middle of the target? And, you know, if you're a good archer, that would be quite a high probability. And if you're a bad archer, it would be a low probability. But it's more like asking, what's the probability we land in a particular area, not at an exact point, which we'd probably have to say was 0. For another example of the same thing, think of picking a random number in the interval between 0 and 1. Again, it doesn't really make sense to say what's the probability of hitting a number exactly. You could say, you know, what's the probability it's exactly 1 over square root 2 or something. Well, that's an infinite decimal, so you'd have to say that the probability of hitting it exactly was 0 again. But what makes more sense is to take, like, a chunk of the interval, like, say, the numbers from 0.7 to 0.8, and say what's the probability that the random number is in that subinterval. And so this is the kind of idea of how we deal with continuous random variables. We don't ask for the probability it hits exactly a certain value, because that probability we'd have to say was 0 anyway. Instead, we look at some interval and say, what's the probability of landing in that interval? And that's how we approach continuous random variables. So we don't have like a probability mass function that gives like blobs of probability on exact points. Instead, we can have a sort of intensity of probability, saying like which areas have the most probability around them rather than which points have the most probability on them. So in discrete probability, we call this mass. You're thinking of like masses of probability at certain points. Here, we kind of think of like the density of probability around a point. So we use the term probability density for that. Although I like to think of it as intensity, how intense the probability is around that point. And we will express this density of probability through what's called a probability density function. So let's have a look at that. So what happens is we say that a random variable x is continuous if the probability that its value is between a and b, so that's for any real numbers a and b where a is smaller than b, can be written like this. We've got an integral from a to b of some function f of x dx. And that f of x there we call the probability density function, or PDF. And so that's the one that's giving us like how intense the probability is, right? Because if that's a big number, then we've got lots of probability in intervals that overlap there. But if that's a low number, then we don't have much probability in areas that overlap there. So you can kind of think of this as like an area under a curve, right? You've got this probability density function, which I should point out is greater than or equal to 0 to make sure we get sensible answers. And like the area under the curve is the probability. I think it's going to make more sense if we look at an actual concrete example. So let's do that before things get too confusing. Let's consider the case where the PDF is 1 for x between 0 and 1, and 0 otherwise. So here, the random outcome is going to be on the interval from 0 to 1, and we're saying that the intensity of probability is the same over the whole interval. So it's like a kind of fair or uniformly random choice. Indeed, this is sometimes called a continuous uniform. Distribution. So if we were to draw a picture of this probability density function, then we'd have the x-axis with 0 and 1, and our random variable would equal 1 in between 0 and 1, and 0 everywhere else. Might put a dotted line there just to show that it jumps up from 0 to 1. That's like saying all the numbers between 0 and 1 are equally likely, although each number itself actually has probability 0, but it's the intensity or the density of probability is the same over the interval. So for example, say we wanted the probability that x is between 0.5 and 0.8. How do we find that? Well, from the definition above, we have to integrate the PDF between 0.5 and 0.8. So this is the integral between 0.5 and 0.8 of this PDF. Now, between 0.5 and 0.8, the PDF is equal to 1, so that's just the integral from 0.5 to 0.8 of 1 dx. If you integrate 1, you get x. It has to be evaluated at 0.8 and 0.5. That gives us 0.8 minus 0.5, which equals 0.3. So the probability that this number is between 0.5 and 0.8, that probability is 0.3. Even though the probability of hitting any particular exact point is 0. Another way to think of that is it's the area under this curve from 0.5 to 0.8. So if that's 0.5 and that's 0.8, then we've like calculated that area under the curve there, which is 0.3, and is that probability. Okay, how about another example? This time, let's call it y this time to keep it separate from the x before. And here it's going to be equal to y if y is between 0 and 1, 2 minus y, y is between 1 and 2, and 0 otherwise. So if we look at this PDF, so between 0 and 1, between 0 and 2, between 0 and 1 it's equal to y, so that looks like that. Between 1 and 2 it's 2 minus y, which is that, and then it's 0 everywhere else. So this is giving us a random variable that takes values between 0 and 2. The intensity of the probability is biggest in the middle of the interval, near 1, and the intensity of the probability is much less out near the edges, near 0 and 2. So we're more likely to get a number kind of in the middle of the interval than we are towards the edges, compared to the last case where the PDF was flat. So again, let's suppose we want the probability that this random variable y between 1/2 and 3/2. So that's going to be the area under the curve between 1/2 and 3/2. So you might be able to actually work out what the answer is by like doing an area of the curve thing, but we'll do the proper integration. Right, it's the integral between 1/2 and 3/2 of f of y dy. Now, here, f of y is defined differently depending on whether you're less than 1 or bigger than 1. Right, so we're going to split up this integral into the less than 1 bit and the bigger than 1 bit and do them separately to allow for the fact that the definition up here is different. So when we're between 1/2 and 1, the function is equal to y dy, whilst when we're between 1 and 3/2, that's 1.5, it's 2 minus y dy. So again, we just need to do the integration. If you integrate y, you get 1/2 y squared. Up to 1 there. If you integrate 2 minus y, you get 2y minus 1/2 y squared, and that goes from 1 to 3/2. And I did put all that into my calculator earlier, and I found that I got 3/4. If you take that picture up there and split it into lots of little triangles, you can see that you're covering in 6 of the 8 triangles, so that's 3/4 as well. So that's another example of how we find probabilities using a probability density function. And the key is that we integrate the probability density function between the intervals we're interested in, and that gives us the probability of landing within an interval for a continuous random variable. In the next subsection, we're going to look at some of the properties that these probability density functions have.